Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on linear algebra, chapter Adjoint and Inverse of a Matrix. Lecture number 9, in which I will use the inverse of a matrix for the solution of system of linear equations. Let we have two linear equations involving two unknowns x and y as follow. A11x plus A12y equal to B1, A21x plus A22y equal to B2. We may write these two equations as follow. A11, A12, A21, A22, a matrix, and here XY, a column matrix, equal to a column matrix B1, B2. Here it is clear that if we multiply these two matrices in the left side, firstly multiply first row with first column A11x plus A12y equal to B1. Next, we multiply second row, here first column A21x plus A22y equal to B2. So this is number 1, this is number 2, this is number 3. So number 3 agrees with equation number 1 and 2. Let A, capital A is a matrix A11, A12, A21, A22, and capital X is a column matrix X, Y, and capital B is another column matrix B1, B2, implies that A capital X equal to B. This is number 4. If determinant of A not equal to 0, that is A is non-singular, then A inverse exists. Multiplying both sides of 4 by A inverse, we get A inverse AX equal to A inverse B. Now associative law, A inverse A X equal to A inverse B. Associative law. And A inverse A is identity matrix X equal to A inverse B implies that X equal to A inverse B. Multiplication of identity matrix with any matrix is that matrix. Let this is number 5. If A inverse B equal to a column matrix C1 C2, then capital X equal to a matrix C1 C2 column matrix implies that capital X is a column matrix XY equal to column matrix C1 C2 implies that X equal to C1, Y equal to C2. In this way, we may find the unknown values X and Y very easily. But condition is that this A matrix, this is called coefficient matrix, this should be non-singular, means determinant of A should not be equal to 0, and we may solve the system of linear equations involving more than 2 variables, that is more than 2 unknowns. Now we solve linear equations with n unknowns. Let we have n linear equations involving n unknowns x1, x2, dot 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 xn as follow: a11 x1 plus a12 x2 plus dot 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 a1n xn equal to b1 a21 x1 plus a22 x2 plus dot 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 plus a2n xn equal to b2 dot 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 an1 x1 plus an2 x2 plus dot 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 plus a n xn equal to bn implies that we may write this as a11 a12 dot 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 a1n a21 a22 dot 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 a2n dot 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 an1 an2 dot 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 ann. This is a matrix, and this is another matrix, column matrix x1 x2 dot 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 xn, and in right side another matrix, column matrix b1 b2 dot 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 bn implies that, let this is matrix A and this is matrix capital X equal to matrix B. Let this is number 1. If a determinant of A not equal to 0, that is A is non-singular, then A inverse exists. Multiplying both sides of 1 by A inverse, we get A inverse under bracket AX equal to A inverse B. By using associative law, A inverse A, here X equal to A inverse B. A inverse A is identity matrix. X matrix equal to A inverse B. Identity matrix multiply any matrix is that matrix X equal to A inverse B. Let this is number 2. Let A inverse B equal to C1 C2 dot 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 Cn, then this X matrix is x1 x2 dot 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 xn equal to C1 C2 dot 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 Cn, implies that x1 equal to C1, x2 equal to C2 dot 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 xn equal to Cn, and we may solve the system of n linear equations very easily. But condition is that this coefficient matrix A must be non-singular. That is, determinant of A not equal to 0, then A inverse exists, and we use this inverse of matrix for the solution of these n linear equations. Now we solve a problem. Problem is, solve the system of linear equations 2x minus y plus 3z equal to 9, x plus y plus z equal to 6, x minus y plus z equal to 2. Now we solve this. Since the system of given linear equations may be written in matrix form as follow: 2 minus 1, here 2, here minus 1, here 3, here 1, here 1, here 1, coefficient 1, here coefficient 1, here coefficient minus 1, here coefficient 1. Here another matrix x, y, z equal to another matrix 9, 6, 2. Let A equal to this matrix 2 minus 1 3 1 1 1 1 minus 1 1, capital X equal to column matrix x y z, and matrix B equal to column matrix 9 6 2. Let this is number 1. Therefore 1 is written as capital A x equal to B. This is number 2. Determinant of A is 2 minus 1 3 1 1 1 1 minus 1 1. Let me find determinant with the help of first column. Here 2 is in the position 1 position, minus 1 to the power 1 plus 1 2. This cancel remains 1 1 minus 1 1 plus, here this is 2 1 position, minus 1 to the power 2 plus 1. This cancel and this cancel, remains minus 1 3 minus 1 1 plus this is 3 1 position. Minus 1 to the power 3 plus 1. Here this cancel, this cancel, this row cancel, this column cancel. Remains minus 1, 3, 1, 1. So this is equal to 2. Here 1 multiply 1. 1 minus 1 multiply 1. Minus 1. Minus 1 to the power 3 is minus. This is minus 1 multiply 1. Minus 1. Here minus 1 multiply 3 plus. Here plus minus 1 multiply 1. Minus 1 minus 3. This is equal to 2, here 2. 2 multiply 2 minus. Here minus 1. Here plus 3. Here minus 4. This is 4 minus. Here 2 minus 4. This is equal to minus 2. This is number 3. Cofactors of first row of determinant A are cofactor of 2. This is minus 1 to the power 1 plus 1. This is 1 1 position. Here we write determinant 1 1 minus 1 1 comma. This is 1 2 position determinant. This cancel and this cancel. 1 1 1 1 1 1 1 1. Now cofactors of 3. This is in the position 1 3. This row cancel, this column cancel. 1 1 1 minus 1. 1 1 1 minus 1. These are, this is 1 1. 1 multiply 1 minus 1 multiply 1. This is 2. This is 0. And this is 1 multiply minus 1. Minus 1 minus 1. Minus 2. Cofactors of second row of determinant A are second row. This is in the position 2 1. Minus 1 to the power 2 plus 1. This column cancel. This row cancel. Minus 1 3. Minus 1 1. Comma. Cofactors of 1. This is in the position 2 2. 2 plus 2. So this row cancel. This column cancel. 2 3 1 1. 2 3 1 1. Now cofactor of this 2 3. Minus 1 to the power 2 plus 3. Here this column cancel and this row cancel. So 2 minus 1, 1 minus 1. 2 minus 1, 1 minus 1. This is equal to minus here. Here 1 multiply minus 1 multiply 1. Minus 1 plus 3 minus 2. Here positive. 2 multiply 1, 2 minus 3 minus 1. This is negative. Here 2 multiply minus 1 minus 2. Here plus 1. Minus 2 plus 1 is minus 1. Here minus. So this is 1. Cofactors of third row of determinant A are third row. This is in the position 3 1, 3 plus 1. This column cancel, this row cancel. Remains minus 1, 3, 1, 1. Cofactor of this minus 1 to the power 3 2 position. This row cancel, this column cancel. So remains 2 3 1 1. 2 3 1 1. This is the position of 3 3. 3 plus 3. This row cancel, this column cancel. 2 minus 1 1 1. 2 minus 1 1 1. This is equal to minus 1 to the power 4 is 1. Here minus 1 multiply 1. Minus 1 minus 3 minus 4. Here this is negative minus 1. 2 minus 3 minus 1 minus 1 minus 1 multiply plus 1. Here this is 1 minus 1 to the power 6. Here 2 minus minus 1 means plus 1. 2 plus 1 3. Let us frame a matrix B containing cofactors of determinant A as elements of corresponding rows. B equal to 2 0 minus 2. Here 2 0 minus 2. Then minus 2 minus 1 1. Then minus 4 1 3. Adjoint A equal to transpose of B. We write this row, first row to first column, 2 0 minus 2. Second row, second column, 2 minus 2 minus 1 1. Here minus 4 1 3. Since A inverse equal to adjoint A by determinant A. Since determinant A is minus 2 and adjoint A is 2 minus 2 minus 4 0 minus 1 1 minus 2 1 3. This is equal to here minus 1 1 2. Here 0 half minus 1 by 2, here 1, here minus half, here minus 3 by 2. This is A inverse multiplying both sides of 2 by A inverse. We get A inverse A x equal to A inverse B, implies that A inverse A associative law x equal to A inverse B, implies that this is identity matrix. X A inverse A is identity matrix. This is A inverse B, implies that x equal to A inverse B, implies that x equal to x, y, z. Column matrix A inverse is minus 1, 1, 2, 0, half, minus half, 1, minus half, minus 3 by 2. And B is 9, 6, 2. We multiply this first row, first column, minus 1 multiply 9 plus 1 multiply 6 plus 2 multiply 2. Here 0 multiply 9 plus half multiply 6 plus minus half multiply 2. Third row, first column, 1 multiply 9 plus minus half multiply 6 plus minus 3 by 2 multiply 2. And by calculating we get this 1, 2, 3, implies that x equal to 1, y equal to 2 and z equal to 3. Therefore, we get our required solution. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button. And if you have not yet subscribed my YouTube channel, then please subscribe my YouTube channel. Thank you.